So today we're going to talk about the fourth step of aerobic respiration, which is called oxidative phosphorylation, and or some of us call it the ETC, the electron transport chain, which is where the oxidative phosphorylation happens. So this is like a brief rundown of what happens during the oxidative phosphorylation, and this is taken from the CIE syllabus. I'm not going to read all this, but it's for a reference for the level of detail you need to know for the CIE exam. But I'm going to explain it. I'm going to explain like the whole thing, the whole process first. Then I'm going to explain the details. And sorry if my English is bad. I have stayed at home for way too long. Okay, so I'm just going to remind you, like right here. I'm not going to the second page yet. I'm going to remind you of the 4 steps for aerobic respiration. Because bear in mind, this oxidative phosphorylation that I'm talking about only happens when there is oxygen present. Because you see, it's oxidative phosphorylation. It only happens in the aerobic respiration, not anaerobic, because, well, it requires oxygen, and this is a process where like a lot of ATP is produced. I believe that you don't have to know the exact number, but just to let you know, in this process, around 28 ATPs are gained. Whereas in the first 3 steps of aerobic respiration, there's not so much ATP gained. So this process is really, really important for you to get like a lot of energy. So the steps for aerobic respiration is as followed. The first is glycolysis. The second is linked reaction. The third is Krebs cycle, or we can also call it citric acid cycle, or the TCA cycle, the tricarboxylic acid cycle. And this is the 4th step we are talking about. The oxidative phosphorylation. Okay, so I'm not going to talk about the first 3, but there are some things that you have to know about it. So you know that NAD and FAD, right? These are what we call as hydrogen carrier molecules. And they're also actually coenzymes. This is something to remember. I think it's going to be really important to the exams because they'll ask you the types of coenzymes that you know about. And while a lot of people know about the coenzyme A and stuff, they tend to forget that NAD and FAD are also coenzymes. Or maybe it's only me, but this is something to bear in mind. And these 2 hydrogen carriers, well, they get reduced during the first 3 steps of the aerobic respiration. So I know that for the NAD, the NAD gets reduced in all 3 steps. So in glycolysis, they're reduced, in link reaction, they're reduced, and in Krebs cycle, they're reduced. But for FAD, they only get reduced in the Krebs cycle. So like after we are done with the 3 steps and we are at the electron transport chain, there are a lot of NADH, but not so much of FADH2. But I'm just gonna write the equations down. So NAD, it undergoes reduction, and it produces reduced NAD. Actually, I just realized I'm missing something. I'm gonna include it here. It gains a hydrogen atom. So why am I calling it reduction here? So if you remember, we can define reduction in 3 ways. One way is the loss of oxygen. One way is the gain of electron. Another way is actually the gain of hydrogen. And the way I remember this is, if you remember the oxygen is lost, the hydrogen is definitely gained. This is how I remember it. And and bear in mind, when the NAD itself is reduced, it is acting as a oxidizing agent. This is going into chemistry a bit. It is an oxidizing agent, and it actually oxidizes the glucose and its intermediates, I should say. Because basically, aerobic respiration is the reaction where we completely oxidize glucose into like several products, right? And this oxidation takes like many steps, and NAD acts as a oxidizing agent for glucose, and it's present in like many occurrences to do the oxidation. So it's there. And let me write down the chemical equation as well. It's NAD. There's actually a positive charge plus hydrogen ion, so a proton, plus 2 electrons to balance out the charge. We'll get a neutral NADH. This is for NAD. And for FAD, it's incredibly similar. So FAD, it requires 2 hydrogen atoms to form, also go through reduction. So again, it's also an oxidizing agent. It forms reduced FAD. This is a word equation. And the chemical equation would be FAD. It also has a positive charge plus 2 hydrogen ions plus, I believe it's 3 electrons, but let me just quickly double check. I think, okay, I'm not really sure here, so a certain number of electrons. I believe it's 3, because only that way it makes sense. And it will form a FADH2. If this part is wrong, then I'm going to probably like correct it in the comment or the description, but I'll just move on for now. Okay, now you know that these 2 molecules, they are actually hydrogen carriers because they take 1 hydrogen away and they bind with it. That's why they are carrying a hydrogen atom, or 2 hydrogen atoms here. So now we reach the electron transport chain, which is built in the inner membrane of the mitochondria. And here, one thing will happen. So let me quickly draw out how the thing looks like. I'm going to do like a really brief drawing. Let me make it just a little bit closer. So this is not a accurate representation of the electron transport chain. It's just merely what's covered in the syllabus. And if you want to know more, this unfortunately doesn't tell you the entire story. I'm also gonna draw like a different thing here. This is a really powerful weapon. You'll know about it later. Actually, this is a bit ugly. I'm a bit, I don't like my own drawing. I'm going to move this to the next page so we have more space. Okay, so this is what we call a electron transport chain, or ETC, if you just like things a bit shorter like me. And here we have 4 complexes, and actually we have several more molecules that are embedded somewhere in this chain, but I'm not going to point these out. So maybe like we have like a few molecules that are not proteins, and we have 4 proteins right here, 1, 2, 3, 4, and we call this entire system, we call it a respiratory complex. I'm actually gonna draw it here. This is called the whole thing is called a respiratory complex. It is a functional unit. You can take it as a functional unit, so like a family. It works together. It passes electrons from one to another. So the first thing that will happen is that the hydrogen carriers with the hydrogens carried on them, so as we know, the NADH and FADH2, these molecules, they are going to bind onto the complexes. And here, the hydrogen atoms will split up, and they'll split to form 1 proton and 1 electron. Which makes sense, right? We have a hydrogen atom, probably something that looks like this. And this is a electron. This contains a positive proton, which is basically a hydrogen ion. So the split happens. So here the same thing happens. The hydrogen, it binds to the complex, and inside here it breaks down into the hydrogen ion and the electron. And after the hydrogen leaves the hydrogen carrier molecules, well, if you guess correctly, this entire NAD and FADH2, NAD and FAD, they're gonna leave because their hydrogens are carried away from them, so it leaves as a NAD molecule, and here it leaves as a FAD molecule. It just returns to however they looked like before taking an hydrogen on their back. And then these molecules, if you guess correctly, they're going to leave the mitochondria. They're going back to the glycolysis, link reaction, and Krebs cycle, wherever they're going. And, well, these are actually recycled in the first 3 steps. So, well, they're not wasted. Let's say it disappears because it goes back to the first 3 steps to carry more hydrogens. Okay, and now inside the complex, we can see that we have protons, we have electrons. I'll talk about the electrons first. The electrons, so one thing I want to talk about is the electrons. They are actually going to be passed along the ETC, and as it gets passed down the ETC, the chemical potential energy of the electrons actually decreases. So let's say this is like the highest energy. The energy is going to decrease, decrease, decrease. And as you know, there will be some chemical potential energy that gets released. And at this point, the electron is already pretty stable. I'm going to explain this part because this is not covered so well in the CIE syllabus. So, okay, although this is not an accurate representation of the ETC, I'm going to call it temporarily like 1, 2, 3, and 4. Complex 1, 2, 3, and 4. Let's just call it that. And let's say I have electron. It's blue colored. Now, there's one thing that's pretty important that I want to tell you, is that affinity for electrons will decrease down the complexes, meaning that the first complex here in the chain is having like the lowest affinity to electrons, while the fourth, the last complex over here, is going to have a high affinity for electrons. So I think a good way to think about it, there are several analogies that I can think of. First one is you can think of it as an enzyme. So let's say electron is let's say it's a triangle. Let's just say it's like a triangle. So now, like, imagine this is like a substrate, and you just imagine that the complex is like an enzyme. Substrate. Complex 1 is like an enzyme. Let's say it's shaped. Let's say it has a really round active site. Well, you can see that I won't call this as a complementary shape. I won't do that. So I'll say the complex 1 has lowest affinity actually for electron. And what essentially happens is that it gets better. The affinity for electron gets better down the group. So maybe, okay, let's say the first complex has like a shape like this, totally out, and it's just not, it just has a really low affinity to the substrate. Second one, maybe it's a little bit better. It's somewhat like a triangle, but like it's a bit round. Third one gets a bit more sharper. It's almost there. And the fourth one is just on point. The electron can bind here most easily. So this is what I mean by the affinity of electron increases down the complexes. So I'm going to erase these because it's not an accurate representation, but I'm trying to show you what I mean. So my point is affinity for electrons decreases down the complexes. Now, what this essentially means is that the electron, they rather bind with the fourth complex than the first complex. So I have like another imagination here. So like imagine this is like a magnet. Imagine this is like a magnet. The fourth complex, the highest affinity complex is like a magnet. And let's say the electron is also like magnetic. And the first material might be the most non-magnetic, while the second gets a little bit magnetic. Third one is even more, and the fourth one is just really, really attractive. So I sometimes imagine that the electrons, they get attracted to the second complex, they get even more attracted to the third complex, and then they get even more attracted to the fourth complex. So yeah, this happens. And there's another point I want to talk about. There's so many points I want to talk about. Well, if you realize, if I say that the electron is most undesired in to bind with complex 1, and if I say it is most desired to bind with complex 4, I kind of imagine it as a chemical reaction. So if the electron has a really low affinity with complex 1, and if the binding of electron with the complex 1 is so undesired, that means this whole complex is also unstable. It won't be really stable because the electron will want to come here, and after that it want to come here. So it wants to leave complex 1. It doesn't want to stay here. Whereas here, where the complex 4 is really desired to bind with the electron, here will be really stable. The binding of electron with complex 4 will be really stable. And hence, well, we know that the word unstable and stable refers to energy. It comes back to energy. So I can also draw like a energy diagram like this. So this is energy level diagram. Let's say this is complex 1, this is 2, this is 3, this is 4. 4 being the most stable. Stable means lowest energy level. The first one being the most unstable and wants to go to a more stable state. This has the highest high energy level, E level. So now you know what happens. Since a unstable complex will try its best, not try its best, it has a high tendency to move to a more stable state. So the reaction happens this way. It just goes downwards. So this is why the electrons, it just naturally passes down from the complex 1 to complex 4. And during this process, we also has a decrease in energy. This is a net decrease in energy. The energy of the electron. What is this energy right here? Well, this is the energy that electron stores, which is called chemical potential energy. So hence, this is why we say, as the electrons are pressed along the ETC, the energy is released. There's energy released from the electron. The chemical potential energy is released from the electron. So now we have another new question, is that where is that chemical potential energy released used? So they're actually used to pump the hydrogen ions across the inner mitochondrial membrane. So from the matrix into the intermembrane space. Let me just write in actual pen. So this releases some energy, right? As I just said. As it goes down the chain, some energies are released. Let's just draw like energy. Some energy. Energy is released. This energy powers the hydrogen ions, and it enables the hydrogen ion to be pumped out of the membrane. So the energy actually fuels this process. So just now, after the hydrogen atoms are being broken down into protons and electrons, now the protons, they're being transported through active transport into the intermembrane space. So just now I forgot to label this. This space is what we called, it's not a space, it's the inner membrane of the mitochondria. And inside here, it's all matrix. Oops. And outside here, it's the intermembrane space. And the outer membrane will be somewhere here, but I'm not going to draw it because it does not play a role. Okay. So this is where the energy released are used. They are used to actively pump the hydrogen ions out of the mitochondrial matrix into intermembrane space. And now, since the inner membrane is not actually permeable to hydrogen ions, meaning that the hydrogen ion cannot exit through the membrane, it has to have the help of a protein, like a protein complex, and energy for active transport. It's not naturally permeable to hydrogen ions. So due to the reason that it's not permeable, and because there is now a high hydrogen ion concentration in the intermembrane space, now we have a proton gradient. So I'm going to draw a proton gradient right here. What I mean by a proton gradient is that there's a lot of hydrogen ions here and not a lot of hydrogen ions here. We have formed a proton gradient or a hydrogen ion gradient. So now so there's something to note, is that apart from a proton gradient being formed, an electrochemical gradient is also formed. So why is an electrochemical gradient formed? So look at this. Just now, don't forget that we have passed the electrons down the chain, and now the electrons are actually still accumulating inside the matrix. They haven't left yet. So there are a lot of electrons inside the matrix actually, and at the same time, there's a lot of H plus outside the membrane. So this actually makes the intermembrane space a lot more positive, and the accumulating electrons make the matrix a lot more negative. And you see, here is more positive, here is more negative, this creates a charge gradient as well. So this is what we call a electrochemical gradient. The difference in charges between the matrix and the intermembrane space, it creates the difference in electro charge. So yeah, we say a electrochemical gradient is established. And actually, I'm going to take a deep breath because now I'm going to explain what happens actually after that. What happens after that? So now, I talked about a proton gradient being formed and also an electrochemical gradient being formed. Both of these gradients, they will drive the protons back into the matrix using this thing called an ATP synthase. Oops. So I'm going to use like layman's term to explain this. You know about diffusions, right? Diffusions are the movement of like a molecule from a region of higher concentration to a region of lower concentration down the concentration gradient. And now, since we have a really high concentration of hydrogen ions out of the inner membrane and a low concentration of hydrogen ions inside the matrix, it's gonna diffuse down the gradient, and also due to the electrochemical gradient here. So that's why I say both gradients are going to drive the protons back. But before it gets driven, I want to talk about something like, this is a really new idea. I actually didn't find it in my textbook. And it's that you can consider the two gradients present as a potential difference. They have a potential difference between them. No matter it's the electrocharges or like the concentration of H+. And this actually means that a gradient, i.e. like a difference, can store potential energy. Well, why do I say it can store potential energy? It's because, well, I haven't explained the ATP synthase yet, but this is how I look at it. I imagine it to be like a, you know, those like hydroelectric water dam. So let's say we have like a really high hill right here. And then we have like a fall. This, like, imagine it as a water stream. Now we have a land. And the action of the water flowing down the stream is actually creating electricity, because the potential energy, let me just quickly draw this out in real drawing. At a high point, like a high altitude, this water, it has more potential energy, PE, and as it rushes down from the high spot to the low spot, it releases kinetic energy. And this also can be maybe, let's say, converted into electricity. I forgot how exactly this works, but I'm just demonstrating this principle. It's actually the same idea here. So this PE, this potential energy, is now built up by the two gradients we have over here. And now, if I let this high concentration of hydrogen ions flow back into the matrix, and I let equilibrium slowly happens, so like the hydrogen ion numbers will be like equal here and here. This is like the equivalent of me releasing that potential energy, converting it to the kinetic energy. Well, so this actually happens. The protons, it flows back through the ATP synthase. And as you might have predicted, energy is being released. The energy that's stored, the PE that's stored in the gradient, is now converted into kinetic energy. As the hydrogens are moving down the ATP synthase. Okay, so since the hydrogen ions are moving through a protein, this is called facilitated diffusion. I'm just gonna write it down. Facilitated diffusion of hydrogen ion. And I talked about the Ke being produced in this moving down. Well, this kinetic energy will actually be supplied for the rotation of the ATP synthase enzyme, like a motor, like a fan spinning. So this kinetic energy rotates the ATP synthase enzyme, and the energy actually, in this way, it helps the synthesis of ATP. So the ATP is produced by ATP plus a phosphate molecule to form ATP. This process needs energy, and the kinetic energy produced by the movement of protons into the matrix actually provides the energy. So this is it. This is like the end of the process, but there's actually something else happened. I'm going to erase this entire part. Wait. You might have forgotten about one thing. And you might think that, well, now I got ATP produced. Isn't this like the end of the story? But no. Have you thought about there's still some electrons being left behind? So where does these electron goes? These electrons, it has to go somewhere, right? It can't be like accumulated in the matrix forever, because if it's there forever, the electron transport chain will not continue to function. It's just stuck there. The reaction isn't really at the end yet. So now we have something called oxygen. The oxygen is actually what we called as the final electron acceptor. So this oxygen, we have an equation. So the oxygen binds with 4 hydrogen ions and 4 electrons. to form two molecules of water. And this water can later diffuse out of the mitochondria into wherever it's being used. So hence, the reaction is now actually complete. And this process of the oxygen binding is called chemiosmosis. So now our reaction, our whole aerobic respiration is actually complete. So let me just write down the equation once more. In aerobic respiration, we use one molecule of glucose, and we have to use 6 molecules of oxygen. So now you know where it comes to play. You see the relation here? This is where it comes to play. And it produces some side products. So 6 molecules of CO2 is produced, along with 6 molecules of H2O, plus a lot of ATPs. So in total, there should be about 32 to 34. I'll write down 34. This is like a theoretical number. Oops, my pen is not writing, but you get my point. So this is it. This is like the whole story of the electron transport chain. And I've explained every little detail that you have to understand